Okay, so our objective for homework 1 is to explain the variation of temperature and pressure with respect to altitude. Some assumptions for this problem. We're going to start with 1 mole of gas, eliminating the need to include moles in our calculation. We have our system is adiabatic, which means there's no heat change, and also our system is reversible, which means the internal and external pressure are the same. And then our equations that we're going to be using, we'll do the statics equation, which is dP over dz is equal to negative rho, which is the density, times g. We have du, which is equal to a small change in heat, minus P dV. We have our ideal gas law, which is PV is equal to RT. And again, we don't need to include moles in this because we're doing 1 mole of gas. And then our fourth is going to be CV is equal to change in heat, change in time, change in heat being dQ, and then also CP is equal to CV plus R. So CV is the heat capacity at a specific volume, and CP is the heat capacity at a specific pressure. Okay, so we're going to start with our law of statics. That was the equation dP over dz is equal to negative rho, the density, times g. Using our ideal gas equation, we can substitute in for density, the dP for dz, which is equal to molar mass times pressure over RT, maintain our acceleration due to gravity. And now what we're going to kind of do is begin to look at the temperature and pressure with respect to dz, which is our change in altitude. So we're going to separate it out and isolate our temperature and pressure variables on one side, and then on the other side we're going to keep our M over RT, G, and keep our, move our dz over. And what we're going to do here is integrate both sides, and this integral right here is from z1 to z2, or altitude 1 and 2. And we're just going to go ahead and solve this integral right now and leave this one for later. I'll explain why. So we have our temperature, pressure, dP, and it's pretty simple. We end up with mg delta z, or change in altitude, over RT. And that's my mistake. Temperature, we moved temperature over earlier. So it's just going to be over R. And basically, now we're going to leave this equation and we're going to solve for our temperature. And then we're going to go ahead and plug in our temperature equation so we can get our pressure equation. So solving for temperature, we're now going to use this equation du is equal to a small change in heat minus P dV. However, since we are assuming that our system is adiabatic, this term is actually equal to 0. So we have du is equal to negative P dV. Since we're looking for temperature, we're going to get rid of P using the ideal gas law. du is equal to negative RT over V dV. And using our heat capacity equation, we're going to get rid of du equal to Cv dt is equal to RT over V. Now we're going to integrate both sides, and we're going to get our temperature over to our right side. So we have Cv times the integral of dt over t, which is equal to negative r integral of dv over v. And this is from t1 to t2. This is from v1 to v2. And actually solving both of these integrals, it's just going to be the natural log. So we have Cv times the natural log of t2 over t1 equal to negative r times the natural log of v2 over v1. And now we're going to use the rule of natural logs, and we're going to move these constants up to an exponent. So we have natural log t2 t1 is equal to natural log v2 v1, and that is raised to the negative r over Cv. And then one final step, we're going to use exponentials to get rid of the natural logs. So we have t2 over t1 is equal to v2 over v1 raised to negative r over Cv. And I'm going to go ahead and wipe the board down, and we're going to start where we left off there. So now that we have this equation here, we are going to use the ideal gas law to get rid of our volume and reintroduce pressure. So that has T, or T1, is equal to RT over P over RT1 over P1, and that is all raised to, again, negative R over Cv. And then with some algebra, we come to T over T1 is equal to T over T1 times P1 over P raised to, again, negative R over Cv. This is because the r's cancel out, and then we're left with this. Now combining like terms to get, again, T over to the left side, we have T over T1, and now that is raised to R over Cv plus 1, and that is equal to, well, we're going to flip the second term so that we can get rid of the negative in the exponent. So that is P over P1 times R over Cv. And now we can make this exponent a lot easier for us to understand. Remembering our equation, Cp equals Cv plus R. This is our heat capacity equation, and that ends up allowing us to say that R over Cv plus 1, which is now the ratio of the heat capacity with respect to pressure and heat capacity with respect to volume. We're just going to replace that and define that as gamma, and we use that henceforth in our equation. So going down, T over T1 to the gamma is equal to P over P1 raised to gamma minus 1. And now we're going to get the exponents on one side. Again, T over T1 is equal to P over P1, which is raised to gamma minus 1 over gamma. And then finally, we can now get our temperature equation, which we're going to be able to put back into the first equation we derived. So T is equal to T1, P over P1, and then gamma minus 1 over gamma. And then now we're able to insert T into our first equation, and we'll be able to solve for our pressure. All right, now that we have our equation for temperature, we can go and plug it in to the first equation that we ended up deriving. And that looks like P1, P2, and then our numerator, T1, P over P1, and gamma minus 1 over gamma, all over P, dP. And then we have constants over on this side, and this becomes important. Well, we have the change in altitude here over R. And since our main focus, or when we insert this equation to our original, the T1 and P1 here are both constants. So we can go and rearrange and basically get all the constants onto the right side, so we can do a much easier integral, and it's a lot easier to handle. So P1, P2, and then this integral just becomes P to the gamma minus 1 over gamma, and all that is to the minus 1. And then on this side, we have negative mg delta z over RT1, and then we have P1 to the gamma minus 1 over gamma. Okay? Now, after we do this integral, it becomes P2, the gamma minus 1 over gamma, minus P1, raised to the same, over gamma minus 1 over gamma. However, this denominator is also a constant, so we can actually go and put it on the right side of our equation. So mg delta z over RT1 times P1, and then gamma minus 1 over gamma times gamma minus 1 over gamma. And that's canceled out from there. Now, the final thing we have to do is basically separate out our P, or P2. So P2 to gamma minus 1 over gamma is equal to, we can get P1 over to this side, P1 gamma minus 1 over gamma is equal to, nope, not equal to, multiplied by, we have negative mg delta z over RT, and multiplied, we have 1 minus mg delta z over RT and then multiply by gamma minus 1 over gamma. And then to get rid of these exponents and to isolate our P2, we move the exponent over here. It becomes gamma over gamma minus 1. And so basically, this is our pressure equation with respect to, notice the only thing that is not a constant is the change in altitude. And if you want to find the temperature equation with respect to only the change in altitude, you can go and insert our pressure into this equation up here, and that will give you the temperature equation.